In this lecture, I am going to discuss on passband pulses. In digital communication, we are going to have to work with signals which are essentially time limited form in some sense. So you have signals and the signals are time limited form. Time limited form. Okay, in some sense, either this time limitation is strictly or at least for all practical purposes. For all practical purposes, we are going to work with a signal which are time limited. Such a time limited signals are called pulses. Okay, pulses. So the specific class of signals which are of interest to us here are pulses. So let us talk about passband pulses and their spectrum. So the goal of this lecture is we are going to talk about passband pulses and its spectrum. That is the goal of this lecture. So first of all, what will passband pulses look like? You know how a baseband pulses look like. In baseband digital modulation scheme, we have taken something called rectangular pulses. Let me call this as P of t. Just take an example. This is an example of rectangular pulse. You know what a rectangular pulse look like. So similarly, what will a corresponding passband pulse look like? It will be a gated form or a windowed form of a simple sine wave. You take a sine wave, one cycle, second cycle, third one, fourth one, and this is time axis, amplitude plus t by 2. It exists between minus t by 2. This is a 0 point. This is your baseband pulse, and this is passband pulse. Passband pulse. So the sine wave is gated or a windowed form. This is a gated. This is also called gated form or windowed form of a sinusoidal wave. Sinusoidal wave. So basically it is a finite duration sinusoid. Look at the duration is finite. The duration is finite. It exists from minus t by 2 to plus t by 2. Such a finite duration signals are called pulses, that is passband pulses. It is a gated sinusoid. It is 0 outside of this interval minus t by 2 to plus t by 2. So if you wanted to define mathematically, it is a sinusoidal function. So in that case, either you can consider sine of 2 pi f naught t or cosine of 2 pi f naught t. Whatever in the time duration between minus t by 2 to plus t by 2. Okay, so in general, its phase may be arbitrary. So we can have a passband representation of this kind as follows. S of t is equal to S sub r of t times cosine of 2 pi f naught t minus S sub I of t times sine of 2 pi f naught t. And this is some kind of rectangular pulse. rectangle pulse or any other shape, it doesn't matter. Now suppose let us denote the Fourier transform of SR of t by SR of omega, small s sub r of t. You take Fourier transform, then you will get capital S sub r of f, and S sub I of t is equal to, if you take Fourier transform, then S sub I of f. Now, what can you say about the spectrum of such a pulse S of t? Now, this is the Fourier transform of your baseband pulse SR of t and S sub I of t. Now, we need to say something about the spectrum of S of f. Let's say this is my passband signal, and you take Fourier transform, then you will get S of f. Now, what can you say about this? You take the now Fourier transform term by term from this equation number, okay? From this equation, let's say this is equation number 1. Take Fourier transform on equation 1. So in that case, you will have capital S of f, that is a Fourier transform of S of t, which is equal to 1 by 2 times S sub r of f minus f naught plus S sub r of f plus f naught minus j by 2 times S sub I of f minus f naught minus S sub I of f plus f naught. So this will have a displacement around f naught. So this guy has displacement, not this one, displacement around f naught, not this one, this S r of f and s, maybe I'll write down neatly, it becomes a little messy. So S r of f and S I of f have displacement around f naught. Suppose let's say your S r of f has the spectrum like this, then this is S r of f, okay, and then this indicates this is S r of f minus f naught plus S r of f plus f naught. So this guy represents S r of f minus f naught, and this guy represents S r of f plus f naught. So the spectrum is displaced by an amount of the carrier frequency f naught. So this is a passband pulse spectrum. So we have seen the time domain passband pulses. So this is a time domain passband pulse, okay, in the time domain, and this is in the frequency domain. But this is a rough figure actually. Originally, if you take Fourier transform, it won't be a rectangular pulse, it will be a sync pulse, because the duration is finite duration, and it is like a rectangular shape. So whenever you take a rectangular pulse in the time domain, if you take Fourier transform, we know that the spectrum looks like a sync pulse. So you will have the shifted sync pulses. So you have one sync pulse like this, and you will have another simples like this, shifted simples. Okay, but anyway, just I have taken some arbitrary shape to show how the spectrum is displaced when you go for passband modulated waveforms, passband waveforms or passband pulses, because here in digital communication we will not talk about a signal which exists for indefinite duration. It exists only for a finite duration of time. That time we say minus t by 2 to plus t by 2. Okay, now let us talk about energy of the passband pulse. Okay, so energy is equal to EP is equal to integral of s square of t times dt. We did not take any modulus here. Okay, no modulus operation. The reason is it's a real signal and the range is from minus infinity to plus infinity. Let me call already what is the equation number. So that is 1. Let me say this is equation number 2. Maybe I can call this is equation number 3. Now by Parseval's theorem, I can find an equivalent expression for this equation 3. So which is integral of s of f. This is magnitude of the magnitude square in the frequency domain, and the integration from minus infinity to plus infinity. So either you take the energy in the time domain or take the area of the spectrum magnitude square in the frequency domain. Therefore energy equal to EP is equal to either you have time domain expression or frequency domain expression, and this will be equal to 1 by 2 times integral of s r of f, the magnitude square times df, plus 1 by 2 integral of minus infinity to plus infinity f sub I of f times df. Let me call this is equation number 3. So equation 3 can be very easily proved. It is a very simple and straightforward exercise in which we express s of f in terms of s r of f and s I of f. Because we know that s of f from equation, use equation 2 and substitute in let me call this is 4 and this is 5, and so let's use equation 5, no, equation 3, and substitute in equation number, I'm sorry, use equation 2 and substitute in equation number 3, no, equation number 4. So that's it. So use the fact, that fact is s r of f minus f naught and s r of f plus f naught will have no overlapping component. So when you come across the product of this guy and this guy, okay, come across the product of these two, the product will equal to 0. So making use of this kind of identity, and if you do some simplification, then you will get this equation. Now the final note is let's say s of f is being band limited. S of f is band limited. Now what can you say about SR of F and SI of F? Are they band limited? Yes, of course. Okay, so these two are also band limited. Band limited. Since SR of F and SI of F have a rectangular envelope, in the sense it is gated by a rectangular function and it has strictly finite duration, the corresponding spectrum is strictly sinc function. See, this SR of t is a rectangular pulse. Rectangular pulse. The pulses looks like this. And if you take Fourier transform, then you have a sinc pulse. Sinc pulses. Therefore, once I say this S of F is band limited, which implies that both SR of F and SI of F are also band limited. So the shape of SR of F and SI of F will be very closely resembled to the shape of SI of F. So this is a simple exercise. One can do that to obtain the expression for SR of F in terms of S of F. So it will be the dual kind of expression that you can have. Okay, so this is a brief introduction or a brief discussion about passband pulses. So in the next lecture, we will talk about passband waveforms for binary signaling, passband waveforms for binary digital modulations or passband digital modulations, how we can use this passband pulses for our digital modulation schemes. So we have many passband digital modulation schemes where we can use this passband pulses. So that we will continue in the next class. Thank you very much.